to introduce our next keynote speaker, Professor Dan Halperin. Professor Halperin received his Ph.D. from Tel Aviv University. He spent, after his Ph.D., 3 years at the Computer Science Robotics Laboratory at Stanford University, and in 1996, he joined the Department of Computer Science at Tel Aviv as an assistant professor. Now he is a full professor at the same university. Professor Halperin's main field of research is computational geometry and its applications. Much of his work concerns geometric arrangements, which are fundamental constants underlying the algorithmic solution of geometric problems in a wide variety of domains. Application areas he's currently interested in include robotics, automated manufacturing, and algorithmic motion planning. Professor Halperin is a very prolific author with publications spanning robotics, computational geometry, and algorithms. A major focus of his work recently has been in research and development of robust geometric software in collaboration with a large group of European universities and research institutes. This is under the CGAL project and the corresponding library. Some of his work is summarized in the Springer book, CGAL Arrangements and Their Applications, co-authored with 2 of his students, Fogel and Wayne, in 2012. Professor Halperin is a co-founder of the international workshop series Algorithmic Foundations of Robotics, and earlier in 2015 he was named an IEEE Fellow. So without any delays, Professor Halperin, please come to the podium.
Thank you, Lydia. I'm very glad and honored to be here. And let me get right away with my talk. To make sure we are on the same page, let me tell you what I think of as the basic robot motion planning problem. We are given a moving system. It can be one robot, several robots. They are moving in an environment which is known to the system, and they have to move from a free start to a free goal position. The problem is then to decide, is there a collision-free motion? And if so, to plan such motion. And you don't have to know much in order to follow my talk. You probably need to know these 2 terms. The degrees of freedom. When I talk about many robots, the number of degrees of freedom will be the sum of the degrees of freedom of the individual robots. And you have to know what configuration space is. This is where we study motion planning problems. We shrink the robot to a point, and in return, we compensate by expanding the obstacles. And the dimension of the configuration space is equal to the number of degrees of freedom of the system. So here's an overview of my talk. I'll give a very brief review of motion planning, just geared towards telling you what I'm concerned with. Then I'll talk about one specific problem that we have been studying intensively in the recent 2 years. And I'll conclude with a few more problems, related problems, on motion planning with many degrees of freedom. So the early days had some rather dark forecast for motion planning because the first result showed that the problem is intractable. Again, you don't need to know complexity classes to follow my talk. When I say that the problem is hard in theoretical computer science lingo, I mean that it belongs to a family, a large family of problems for which no efficient solution is known, and the best possible assumed for now is algorithm that run in time exponential, in this case exponential in the number of degrees of freedom. And Schwartz and Sharir in their famous piano mover series showed that you can in fact solve any reasonable motion planning problem, but in time that is doubly exponential, meaning that the number of degrees of freedom appears in the exponent of the exponent. Then came John Canny, and he gave a general, complete solution, which is only singly exponential. I tried to give you a graphical representation of the feeling that time, that the problem was very, very hard. With limited PowerPoint skills, I'm trying to show that it's harder when the number of degrees of freedom is bigger. But still, it seemed that everything is difficult. I spent 5 years in my PhD trying to give efficient solution to motion planning problems with 3 degrees of freedom. On paper, they are still the best possible, but I can tell you that they are horribly complex, and no one in their right mind would try to implement them. So back then, it looked not very promising, but there was a parallel world, and people didn't wait for this theoretical result and started developing practical motion planning solutions. And the big boom was the mid-90s with probabilistic roadmaps, and it has never stopped since. And these sampling-based techniques can now solve problems with literally dozens and even hundreds of degrees of freedom. And my question is, what's going on here? Is it a hard problem? Is it an easy problem? So we talk a lot about narrow passages. When is a motion planning problem hard? Where there is a narrow passage to get from the start to the goal in configuration space. Again, trying to give you a graphical feeling for what's going on, it was obvious that you need to add another dimension to the discussion of motion planning algorithm, and this is the x-axis here. So near zero, the left-hand part is sparse motion planning problems, and on the right-hand side, it's dense motion planning problems, where the robots move in contact with the obstacles. And sampling-based algorithms show that there is a light in this dark tunnel, and if your problem is not too dense, you can probably solve it rather easily. But let's try and formalize what it means to be easy or hard. So one place to look at is probabilistic completeness results. These are the results that tell you that your algorithm will find a solution eventually. Eventually may be the end of time. You don't know exactly when, but at least they promise you that you are on the right direction, which is not little. Now, as you may expect, the needed number of samples in those algorithms is inversely proportional to the radius of a sleeve, the sleeve of free space that we assume around the path. But there are a few problems with this observation. One is that it's very difficult to compute this width. It seems almost as difficult as solving the original motion planning problem. Also, as I will try to argue, this might be asking a bit too much. So let me now go to a problem that we have been investigating in the last 2 years, where we believe we are getting closer to this quantitative distinction between hard and easy problems. First, let me mention some generalization of multi-robot motion planning that we introduced a couple of years ago. We call it the K-color multi-robot motion planning. In the picture, you see 7 robots, yellow, blue, red, moving in a planar workspace where the obstacles are gray, and they are arranged in 3 groups. And in the K-color motion planning problem, we don't distinguish the robots within one group. And there are 2 extreme cases of this problem. One where K equals M, and this is the standard motion planning problem. I call it the fully colored. And the other extreme is when you have only one color. All the robots are indistinguishable. They have the same geometry, and I don't care which gets where, to which target position. So we are not the first to study this problem, and in fact, the Halperin and al result, I'll talk a little more later. Now, let's focus on unlabeled motion planning and make sure that people understand what it is. So I give you unidisk robot, say. The green denotes starting position. Purple is target position. And I don't care which robot gets where at the end. I just want all the target positions to be filled. I'll actually make a few more assumptions about the problem that I'm solving. I give you M interchangeable disk robots. They are moving inside a simple polygon with n sides. Each of the M goals needs to be occupied at the end. This is the unlabeled version. But I make one additional assumptions. The robots in the start and goal position have 2 units space between them. And if you look at the centers of robots, they have 4 units between them. I take all the start and goal position, and I make sure that each pair abides by this rule. So here is an example problem. You have a simple polygon, start position, goal position, and the assumption is these expanded disks are pairwise interior disjoint. And for this problem, we give a complete combinatorial algorithm that runs in time n log n plus mn plus m squared, a far cry from the exponential prophecy. And I want to explain a little what is going on, and let me give some technical details. So I start with a simple polygon, but I look at the free space of a single robot. This is, I shrink the polygon by unit 1, and this is the free space. The free space is no longer one connected component. It may break into several connected components, which I denote by Fi. And the algorithm, the efficient algorithm, stems from 2 observations. One, inside each connected component, there is a very nice behavior. And the second one is that robot in one connected component can obstruct the motion of a robot in a different connected component. But if you look at the connected components, this bad influence doesn't create a cycle. So a robot in Fi can stop a robot in Fj from moving, and a robot in Fj can obstruct a robot in Fk. But then Fk cannot disturb Fi, and you cannot get cycles. And with this, we are able to give a very efficient algorithm. And the question is, again, what's going on here? Why is this specific problem so easy? It's easy, the analysis is not easy, but it's easy as compared to hard problems, intractable problems. It has a quadratic solution. And here are possible suspects for this problem being easy. Is it because the workspace is a simple polygon? It is homeomorphic to a disk. It doesn't have holes in it. Is it because it is an unlabeled variant? Is it because the robots are so simple? Or is it because of the extra separation assumption? So now let's take each of these assumptions and examine them. Is it because the workspace is homeomorphic to a disk? Well, the answer is probably not. And over 30 years ago, Spirakis and Yap showed that motion planning problem for disks in a single polygon is NP-hard. It's still different from our problem because the robots are labeled. The proof actually relies on the fact that they have different radii. So perhaps this is because it is the unlabeled variant. I can tell you for a long time, this was my prime suspect, that unlabeled motion planning is easier than labeled motion planning. Well, this is not the case. We have recently shown that unlabeled motion planning for unit squares in the plane is p-space hard. This is going to appear in the forthcoming RSS. Let me tell you a few words about this result. First of all, it's the first hardness result for unlabeled motion planning, but interestingly, it also applies to labeled motion planning. And then again, it's a first, because it's the first that uses one type of robot for hardness. Earlier multi-robot motion planning result, it started with, in 84, with many different type of robots. It got smaller to 2, and this is the first one that uses a single type of robot. And it's amazing how simple the problem can be and still be hard. We prove hardness for 4 different variants of the unlabeled motion planning, and one of them is I give you M identical robots, I give you one target, and I ask you to move any robot that you wish to this target. Even this problem is p-space hard. And behind the scene is a beautiful result by hand and the main. Here is a take-home advice that I can give you if you're interested in hardness of robot motion planning or of games. They came up with an elegant and powerful mechanism called non-deterministic constraint logic, from which it is fairly easy to derive hardness result. Let's continue with checking the problem, the unlabeled problem that we started discussing. Is it easy because the robots are so simple? Now, we already know that this is probably not the reason, because the problem for unit squares is p-space hard. So is it easy because of the separation assumption? Yes. This is probably the reason why this problem is easy. Now, you may think that I got back to square one, to the sleeve required by sampling-based algorithm, but I argue that this is not the case. First of all, notice that the separation refers only to 2 static configurations, the start and goal. I don't say anything about the path. I don't assume anything about the path. Secondly, we do not require clearance from the obstacles. The start and goal can be attached to the obstacles. Okay, so separation is crucial here, and there's an interesting side effect in our analysis. And it's a very simple decision procedure that tells you whether the problem is solvable or not. If each connected component of the free space has an equal number of start and goal position, then there is a solution to this motion planning problem. So I assume the separation of 4, and this gives me a very simple decision procedure. And now the question is, does it always hold for any separation distance? And we have shown that it doesn't hold. If you go below 3.6, then even though you have the same number of start and goal position in each connected component, your problem might not have a solution if you have a separation of less than 3.646 between the start and goal position. So what I mean by closing the ring, I think that we have put a siege around this unlabeled motion problem from many directions. It is not yet completely settled. When would I consider it settled? First of all, we still need to show that the problem for disks is hard. It's hard for unit squares, but I don't know yet. I believe it is, but I don't know yet that it is hard for unit disks. And here's an example of the type of solution that will interpolate between hard and easy problem. So if I keep a distance of 2 between start and goals, this means that the robots are touching. Now I add an epsilon to these 2. And I would like to get a good solution to the problem, not only in the dimension of the configuration space and the complexity of the workspace, but also in 1 over epsilon in this separation. So I hope that this problem will yield soon, but it is still open. Okay, let me make a few remarks about motion planning with many degrees of freedom. If we leave the basic problem and we move to optimality, the problem becomes much harder. We know it from other areas of motion planning. So again, I have unlabeled disks, and I want to get good paths. There are two results along this line. One by Turpin et al. They optimize the length of the maximum path by any robot in this problem. We gave an alternative optimization. We approximate the total travel time. Each of these results makes slightly different assumptions. You should distinguish between these problems and the analogous problems on graphs. There is a big literature, but I'm referring to configuration spaces with volume. I want to say a few words about our optimization result. The algorithm is implemented in an exact manner. It uses the Computational Geometry algorithm library, and with the tools available there, it was rather easy to give a deterministic exact solution. And if I go back to my graphic depiction of the state of the basic motion planning problem, I would say that 2 degrees of freedom for fairly general robot systems is solved even in the tightest settings with the algorithms, the combinatorial algorithms and the algebra supplied by CGAL. Actually, every reasonable motion planning problem with 2 degrees of freedom can be solved even practically. Now, you might be worried that I only take care of unidisks in the plane. So no, we and others are also concerned with more complex settings. I'm not sure it will have much effect on the hardness result, but we came up with a method to efficiently cope with complex systems of many robots moving in 3-dimensional space. We call it discrete RRT. It enables to efficiently handle the tensor product of many small configuration spaces. There is a competing algorithm, M-star by Wagner and Chauset. Each of the algorithms performs better in different situations. Okay. On a more personal note, I started my work in robotics in automotive factories. I was concerned with making the tip of the robot arm follow a straight line or some given path. We called it motion planning back then, although there were no obstacle, no nothing. It was just about careful and economical use of inverse kinematics so the robot tip follows the path nicely. I was excited then about manufacturing and automation. This is a picture from several decades ago, and I'm still excited about these problems, but unfortunately I find that students, at least around me, but I believe it's a global phenomenon, look at manufacturing automation as the less sexy sibling of robotics. This is a grave misconception, and I will conclude my talk with 2 exciting problems on motion planning with many robots in manufacturing. So problem 1, I colored the multi so you be sure that it is not a typo. What you see here is a picture from a factory in Barcelona, and they wanted to compactify some packaging station that has several robots leaning over a conveyor belt. Now, this was computationally a major change because previously the robot workspaces were disjoint. And after the compaction, they become intersecting. So what we managed to do, we managed to develop real-time collision detection for the system and even deploy it on a controller with very limited storage. This will appear later in the summer in case. What we really want, and what is the big challenge, is to do real-time motion planning for this multi-robot system. And finally, let me suggest another interesting problem from the domain of 3D printing. So people don't know it, but 3D printing has been around for over 30 years. It's been catching up only in recent years, and actually nowadays it's moving from prototyping to manufacturing. 3D printing is an umbrella name for many technologies, but almost all of them have some printing head, dropping material. It can be plastic, it can be epoxy, it can be a laser beam, and printing the object one layer after the other. Now, it is a very slow process. And one way to speed up the process is to use more than one printing head. And some technologies use hundreds of printing heads. But almost always, the printing heads are rigidly attached together, like on the left-hand picture. If you really want to save time, you would like the printing heads to move independently. So I go to some extreme on the right-hand side with two robots printing a sand bridge, but you can think of many printing heads moving inside a reasonably sized printing volume. Now, this problem, in addition to obeying various constraints imposed by 3D printing, has the difficulty and the beauty of multi-robot motion planning, a very challenging problem. Let me thank my students, and in particular Kirill Solovey, who is the major force behind several of the recent results that I mentioned here. Acknowledge my funding agency, the Israel Science Foundation, the EU, the German-Israeli Foundation, the other ones are spelled out, and also my many collaborators. I see quite a few of them here in the room. I'm afraid to mention names because it's really a long list. It's been a very supportive and helpful community, and I thank you for that, and I thank you for listening.
Thank you very much for your presentation. We have a little bit of time for questions, and I would like to invite you to ask questions. I will try to bring the mic to you. Okay, Professor Goldberg.
Thank you, Professor Halperin, for such an inspiring talk. Of course, I have to disagree with you about automation being interesting, but otherwise, I want to ask, what about the question of uncertainty in shape, in motion?
As you know, it's very, very difficult. The point that I wanted to make here today is that even the basic problem is hard.
It just gets harder, you mean?
It gets harder. You can typically rephrase it in geometric terms, but it only makes the problem harder and sometimes much, much harder.
And do you think there's some interesting problems, though, in modeling that uncertainty and sort of being able to think about it with the computational geometry approaches?
Say it again?
Could computational geometry offer insights into modeling this uncertainty and being able to cope with it?
It did, and there is ongoing work on uncertainty, only on the very basic geometric constructs like convex hulls. It will take some work to extend it to motion planning with many degrees of freedom.
Okay, do we have another question from the audience? Okay. As a comment, I'm always amazed how you manage to start from a very basic problem and then generalize and generalize. And I was very surprised to see in your talk this idea of closing the loop using the multiple robot example. So do you think there is still light at the end of the tunnel for the high degrees of freedom problem in constrained spaces?
Yes, I think we must keep some level of optimism to get us going. Yes, I believe there is hope.
Okay. Anything else from the audience? Okay, if not, we are going to conclude this session. Please join me in thanking Professor Halperin